Okay, hello everybody. So today we continue to talk about the induction motors. So first of all, we would like to talking about the motor developed torque issues. So as we show here, I still remember that in lectures we have based on the equivalent circuit, per phase equivalent circuit, we have derived that the relationships between the induced torques and the motor slip. So generally, if the motor is in the running mode, the slip is much smaller than 1. So at the moment of starting, the slip is close to 1. So in case is small, much smaller than 1, then and x1 are small, okay. So in case that the slip much smaller than 1, and also the x1 much smaller than x2, actually the x1 x2 can combine together as a reactance x. Then the R1 usually much smaller than the R2 over x. So in that case, the torque slip relationships can be simplified as this is the simplified So we have the simplified torque slip relationship. Here we just need to know that 1, the per phase applied voltage V phi, and R2 here, which is the motor's resistance. Usually it is constant. Refer to the stator. S here is the slip, and the omega synchronous here is the synchronous speed, which depends on 1, the frequencies the current applied, and 2, the pole numbers of these stators. So then x2 here actually is the leakage reactance of the motor, referred to the stators. So here, because that we are talking about the slip much smaller than 1, generally, for examples, if the motors achieve the maximum torques, so that points, maximum torques, that points we call it breakdown, breakdown points. So in the breakdown points, so there is a slip. So the slip we call it breakdown slip. Torque maximum breakdown point. Breakdown point. So at the breakdown point, so when we're looking at check about the torque slip equations here, under what conditions that the torque has the maximum points. So obviously, look at these equations. If the slip is too small, then so R2 over S, and here R2 over S squared. So if the R2 over S very small, so S very small, RS over 2 will be very large. However, so the denominator here, which is square, numerator R2 over S. so cancellation 1 of it, so making the denominator, right, very, very big, very big. Okay, so the torque will be very small. Okay. And similarly, if the slip, right, too big, then making the more torques small again. So at the moment that the R2 over A is equal to X2, equal to X2, then this, right, functions has the maximum values. So therefore, generally, so the maximum torques occurs at the moment that the slip equal to R2 over X2. X2. Over here, so both the R2 X2 just represent the physical constant of the motors, not exactly represent the rotor resistance or motor speeds. Anyway, for a given motors, there are so R2 and X2 are two constant. R2 and X2 are two constant. Even more, so R2 X2, if you once you have the motor be made there, so the R2 X2 are two constant. So R2 more days equal to the motor's rotor resistance, referred to the stator. X2 more or less, right, equal to the leakage reactance of the motor stator, referred to stators. So, but not exactly their values. But anyway, so here just the two parameters to represent the motor's physical phenomenon. Okay, so then, so for two constant R2 X2, so if the slip, so equal to the ratios R2 or X2, then the motor usually has the maximum torques. Maximum torques. Therefore, so maximum torques occurs at these points. So when at the maximum torques, because the R2 over the slip equal to X2 at the moment. So then the above formulas can be further, right, simplified with this one. Generally, the motor's internal resistance R2 much smaller than the reactance X2. As a result, imagine that the slip, breakdown slip, SB here usually is, right, much smaller than 1. Generally, for most motors, so these values, right, less than 0.5, say 0.3, 0.2, or 0.15, and so, generally that the breakdown slip, right, for a motor in commercial motors, that the breakdown slip usually is smaller than 0.5, typically is about 0.2, something like that, and because that R2 always smaller than X2. So with these conditions, that the motor has the maximum torques, and the maximum torques as can be expressed as, right, the functions of the breakdown slip. Here, breakdown slip is the ratio R2 over X2. R2 over X2. So you can write breakdown slip bring in, that is R2 over X2. So which making the X2 just be there. So that's the breakdown, maximum torques, the breakdown maximum torques. That this is one thing. On the other hand, so if the if the slip, right, is much smaller, even that the R2 over A is much larger than X2. I.e., plot case. Then, so if the R2 over A is much larger than X2, for examples, the full-load case. In the full-load case, the A's may be 0.05, something like that. Okay. So generally, for most of the motors and the full-load case, it's right. Okay, slip be smaller than 0.1, typically around 0.05. So in such a way that R2 over S is typically much larger than X2. Then the X2 can be ignored further, and we can have, okay, so the induced torque and full-load case, okay, full-load case can be written like this. Okay, so this is for, okay, between the non-load and the full-load case. Okay, full-load case, we have this. Look at these three, okay, formulas that they just used to represent, okay, their relationship between each others. Okay, compare that the maximum torque and the induced torque and full load. So they are very similar to each other, the formulas. But look at here. So 3V phi square SB over 2 times omega signals R2. But look at here, the induced torque and full load, or between, okay, smaller than full load, that 3V phi square slip S over, okay, no factor 2, omega sequence R2. So you have factor 2 here, but no factor here. Okay, but here you just have 3 here. This is for 3-phase issues. Okay, 3-phase issues. So based on such a relationship, in practice, we can take measurements about the torques and, okay, powers of the motors and full load, or at the points of the, okay, breakdown points, so that we can determine the internal, okay, parameters, or based on internal parameters given, we can determine under what conditions and what points that the motor has the maximum torques. So with this in mind, and also in the basis, okay, that what we talk in next week, so we can looking at the following examples. The first example, example 4. Now, so looking at these examples to see how to apply the above knowledge to answer, okay, these questions. Example 4, a 4-pole 37 kilowatt 208 volt 3-phase induction motor has a starting torque of, okay, 225 Newton meter and instantaneous starting line currents of 700 amperes, okay, block motor, and a rated voltage, of course, and a rated right frequency. A reduced 3-phase voltage of 120 volts AC is applied to the 9 terminals. Calculate 1, the starting torque, 2, the starting currents. This, right, okay, exam you are understanding about the motor starting issues. Okay, so at the moment of motor startings, that the motor currents proportional to the voltage applied to the motor steers. So the relationship, okay, is that, okay, the current proportional to the voltage, okay, and the torque is proportional to the voltage square. So this is the general situations of the motor issues. So from this point of view, for this given motors, so if the voltage be 208 volts, its right starting torque is 225 Newton meters. Without changing of the frequency, okay, it just the voltage has been down to 120 volts. Then the starting torque also will down to certain values. So because the frequency no change, the signal frequency no change, so we can simply that using a right relationship that actually I draw on the during the exercise actually. So I write down something there like this. So the starting torques at voltage V proportional to starting torques at the voltage V original values. So in square here. So original values, original voltage. Now the values, now the starting torques. The original values at 208, the torque is 225 Newton meters. Now the voltage down to 120. So 120. So the new starting torques will be smaller, proportional squares of the voltage ratios. Voltage ratio square again here. So the new starting torque will be 75 Newton meters. That means if we're using the reduced voltage method to start torque motors, then the starting torque will also reduce. So if the voltage reduced halved, then the torque reduced 1/4 of it. That's it. Now, similarly, starting currents. Remember that the current proportional to the voltage. If the frequency is no change, if the internal parameters, of course, no change. So R1, X1, R2, X2, then there always no change. So then, if the voltage down, then the current's down. Here, the frequency no change. Okay. So generally, so at the moment starting, the slip is equal to 1. Okay. The resistance and reactance constant. Okay. So they are constant. And then the starting torques proportional to the phase voltage square over the sequence speed. Remember this one. And the current, the starting currents. Okay, so starting current equal to the impedance, right? Okay. So the starting current proportional to the voltage, right, over the impedance. The impedance usually is constant. Okay, so for given motor and the moment starting. So that's why we have this one. Okay, so this gives, right, okay, so that's the meaning of it. Example 4 for the starting issues, telling you to write special issues. Now, example 5, it says that 8.60 Hz squirrel cage induction motor is deliberately loaded to a point where the pull out or stalling will occur. Pull out or stalling will occur means that they get maximum torque points. Okay. Okay, this means that the pull out or stalling will occur. This is maximum torque points. Okay, the rotor resistance per phase is 0.3 ohms. This is a rotor resistance per phase is 0. That means referred stator. Okay, and the motor stalls at 50 rotation per minute. Okay, so that means that at the moment that the motor has the maximum torques, its rotation speed is 650 rotation per minute. Okay, this is the question. Now, please calculate A, the breakdown slip, and B, the locked rotor reactance, the static still reactance, that means the X2, and C, the rotor frequency at the maximum torque points. Okay, first, what does it mean by the slip? The slip is the motor speed over the signal speed, right? That's the slip. So here we know that this motor is 8-pole 60 Hz squirrel cage induction motor. So the signal speed can be simply estimated using the frequency and the pole numbers given. So using the formula 120 frequency over the pole numbers. So 120 times 60 over 8 poles. That's 900 rotation minutes. So therefore, now at the moment, the motors has the maximum torques, the slip, that is the breakdown slip, which is the synchronous speed, the different synchronous speed over the motor speed and minus the motor speed over the synchronous speed. So which can be found out. So it's about 0.278. So this is the breakdown slip. Breakdown slip, which equal to x2 r2 over x2. Okay, that's this one. At the moment that the motor has maximum torques, so at the moment the slip equal to R2 over X2, the motor has the maximum torques. But now by observations, we found that the motor has the maximum torques, or the motors has the stalling phenomenon occurred. So then the rotors has a speed 650 rotation per minute. while that synchronous speed is 900 rotation per minute. Based on this one, and the stalling moment, the motor has a slip 0.278. This is just the breakdown slip, which is equal to R2 over X2. So now R2 is given. So X2 can be easily found out without anything right to be wrong here. So without thinking, you can got the breakdown slip, and those you can go to X2. So the X2 is the locked rotor reactance referred to stator. That means which is a constant, as I explained when we're talking about the equivalent circuit. Okay, so locked motor reactance therefore can be estimated X2 equal to R2 over the breakdown slip, which is we calculated in the part A, 0.3 over 0.27, which is about 1 ohms. So 1 ohms, of course, much larger than 0.3 ohms of the reactance, resistance. And also the rotor current frequency, so which is the slip times the frequency of the stator currents. This moment and the breakdown points, the slip we calculated, and the frequency of the current induced on the rotor can be estimated, which is about 16.7 Hertz, which is different from the current frequency applied on the stators. But anyway, so both example 4 and example 5 are the straightforward examples that demonstrate you the concepts we just learned. Now we come to the example 6, which a little bit some mixtures of the concepts we learned above. Okay, let's looking at example 6, and also in your mind, we should have the concept of equivalent circuit. We also write child brace to understanding the relationship between the starting torques, between the maximum torques, and between the starting torques, maximum torques, full load torques, as well as the internal parameters R1, R2, X2, and so on. Now, the values given here is the testing values. So a 25 horsepower, 380 volt, 3-phase, 50 hertz, 2-pole induction motors. So this sentence give you all the information on motor cells. Develops a maximum torque, develops a maximum internal torque of 300% of the nominal torque, and to slip of 24% when it is operate at a rated frequency and a rated voltage. So first, this motor has a nominal or full load or rating powers 25, output powers 25 horsepower. That's what I mean. 25 horsepower is output powers at the full load case. And the 380 volts is the 9 voltage applied on the stator, and it is a 3-phase motor, and the current of the frequency is 50 hertz, and it is this 2-pole induction motors. So it has a maximum torques that 300. That means 3 times of the rating torques. And slip of 24%, 0.24. Then this means that the breakdown slip this is the breakdown slip. This is the rating torques, maximum torques. Okay, so that's the meaning of it. Okay, this motor has an output torque and full load 25 horsepower. The applied voltage is 380 volts 9, 3-phase, 50 hertz. The motor is a 2-pole induction motor. So at the moment that the sleep be 0.25, okay, breakdown, okay, sleep, it has a maximum torque. So the maximum torque is 3 times of the nominal torque. That's the conditions given. Okay, that's the observations from the motors. Now, based on the above, right, theories or concept you learn to determine A, the sleep and full load as the full load speed. The sleep and full load sleep. Okay, now because we do not know, right, full load sleep, because the questions does not tell us that information. And B, the rotor copper loss and full load. And C, the full load torque and starting torque. The full load torque and starting torque. So how much is the torque? Nothing given there. Okay. So however, based on what we learned, okay, above, so we can, based on the information given here, estimate the ABC. The question also said that here, stator and rotation loss may be ignored. Okay, so actually we ignore the stators, okay, R1. Okay. What does it mean? Stator R1 is 0. Torque induced equal to torque output. That's the meaning. Stator and rotation loss may be ignored. Then stator, okay, losses, that is the, okay, losses R1 equal to 0, ignored. That means rotation losses being ignored means that the induced torque equal to output torque. Right? That mechanical, right? So there, the torques, okay, ignored. Now, rotor resistance may be assumed constant. R2 be a constant. That's the meaning of it. Get understanding of it. So look, this example totally different from the example 3 that we considered, right? We started last week on the equivalent circuit. Okay, so based on the side-to-right explanation of the question itself, let's go ahead and see how to find out, one, the sleep and full load, and the full load speed. Now, first, we know that if we ignore the stator and the rotation losses, then the maximum torques, internal induced maximum torques or output maximum torques is the same. So which proportional to the voltage square, 3 times of it, okay, breakdown sleep, and 2 times the synchronous speed, and R2, which is the rotor resistance, which can be seen as a constant. This is the maximum torque issues. Now, the full load torques, as I just said, that full load torques can be simplified as 3 times the, okay, per phase voltage square, the sleep, okay, over the synchronous right speed, and R2. That the question given that maximum torque equal to 3 times of the, okay, max torque equal 3 times of full load torque, and the breakdown sleep is 0.24. Okay, the question is given speed 0.24. So based on this relationship, T maximum equal to 3 times T and full load. So we can find out the full load sleep by comparison the T maximum and the T given here. So because the V is the same, synchronous speed is the same, R2 is the same, which be cancelled between each other. So we bring, okay, the formula here to here and the formula here to here. So we can find out the full load sleep is related to the breakdown sleep, okay, SB, which actually, okay, the breakdown sleep, okay, divided by, okay, 2 times 3. So the full load sleep, which can be found to be 0.04, while that breakdown sleep, which is given 0.24. Okay, so this is the full load sleep, can be simply estimated based on the, okay, these two simplified formulas. Then, so for 2-pole machines with 60 hertz, 50 hertz, so the sequence speed is 3,000 rotation per minute, or that the sequence speed in the rating per second is, okay, 314 rating per second. Okay. Then the motor speed, which is the, okay, sequence speed times 1 minus the full load sleep. So in this case, that's the rating speed of the motor and full load, okay, with the sleep 0.04 and the speed 2,880 rotation per minute. And also you can convert this, okay, speed into the, okay, in the units of the radians per second, which is about 301.4 radians per second. You can examine this one. So this is the part A, that we successfully obtained the full load sleep, that is 0.04, and the full load speed, that is the 2,880 rotation per minute, the corresponding values in the radians of the second. For part B, that as you know, that full load rotor couplosis, is the 3 times I2 squared and R2. So the R2 now we didn't know, and I2 we also didn't know, but it is given that the full load output power is 25 horsepower. On the other side, that we know that the output powers equal to the, okay, right, air gap powers. This is air gap powers. Okay, sorry, output powers. This is the converted powers. So ignoring the equal to output power. So ignoring the stator and the rotation losses, then the conversion power is equal to output powers. So the conversion powers, okay, so output powers, that is the, okay, these parts, okay, output powers. Sorry. Bus, rotor, okay. So if you're ignoring that stator and the rotation losses, then the conversion power is equal to the out powers plus the rotor copper losses, which is 3 times I2 squared and R2 over S. Among it, that the copper losses is the 3 times I2 squared I2, and the output powers is 3 times I2 squared I2 times 1 minus S over S, okay, which is the over S. So this is the losses. This is losses, copper losses, stator copper, rotor copper losses, okay, and this is the output powers, and this is the converted powers, okay, converted powers, okay. This is the air gap powers, converted powers. Okay, so if we ignore the stator and the rotation losses, their air gap powers equal to the conversion powers plus rotor copper losses. There, the conversion powers actually is the output powers. Sorry, output powers, which is this one, this one. So therefore, the losses, copper losses, as we get written here, and the output powers, which is the converted powers. Output powers or converted powers, related to the power losses like this, while the slip. So we have no necessary to calculate R2 here. We just to find out relationship between the output powers and the internal copper losses. So the slip now we have calculated in the full load is 0.04, and the output powers is given 25 horsepower. So each horsepower is about 746 watt. So therefore, the loss can be copper losses. The full load rotor copper losses can be estimated about 777 watt, which larger than 1 horsepower. That's the meaning of it. Furthermore, so we can estimate the starting and the maximum torques. The part C, if we ignore the rotation losses, the full load induced torque is given, that is the output torques actually. So the output powers is given. That now the motor speed has been estimated in part A. So we should use in the radians per second values. So motor speed, 301.4 radians per second. And the output powers, which is given, so 18,650 watt over the 301.4 radians per second. So we can estimate output torques 62 Newton meters and full load. No mechanical losses. So if there is no mechanical losses, then the induced torque or output torque is the same, right? So because the difference comes from the mechanical loss, right? Okay, that's the meaning here. That's why in most of the case, we just directly analyze the internal induced torque, because the internal induced torque represents whether the motorist is powerful or not powerful, right? So minus the losses will be the output torques. So here, so we can estimate the output torques and 62 Newton meters. Now, at the moment starting, so slip equal to 1. Okay, for this case, slip equal to 1, and x2 equal to, because we, from the breakdown slip is given, so 0.2524. So therefore, what does it mean by breakdown? Breakdown means that x2 equal to r2 over 0.24. Okay. If we ignore the stators, then we can simplify that. The start torques related to the motor frequencies and motor resistance. So here the R2 over 1, then x2. The x2 can be replaced with the R2. Okay, so we just need to find out. So the R2, the R2, the R2, the R2. R2. So finally, we just got that. The starting torque equal to the 3 times v squared and times the coefficient over the omega signal speed R2. And meanwhile, that this is the full load torques. Look at full load torques. This is the starting torques. The full load torque, starting torque. So compare this with this one. We can find out the starting torque is about 1.36 times the full load torque. Okay, the full load torque here, slip is 0.04. And now the starting torque here is 0.0545. Okay, because we obtained here. And the voltage V is the same, R2 is the same, signal speed is the same. Okay, signal speed is the same. So compare these two. So one can get that the starting torques is the full load torques 1.36 times. So the full load torques we estimated here, and the starting torques we can estimate it by times the 62 with 1.36. So we now get the answers for the part A, B, C. So here we not necessary to know the values about I2, not necessary to know the values R2, not necessary to know the value X2, but we can obtain that's the torque, obtain the speed, obtain the slip, and so on. So this is example 6, that very interesting, quite different from that of the example 3. The fix here is about the torque issues. The starting torques, the full load torques, the breakdown point torques or stalling torques, or we call it the maximum torques. That's the meaning of it. So so we had better stop here today. So because that you need a time digest of this one. Digest of this one. If you still have some questions, you can write down on the chat box, or you can write to me using the emails after the tutorial sessions, or even can you ask me during next lectures, so in our Monday lectures. Anyway, do not hesitate to ask me questions on whatever the subjects, So I'm very glad to answer your questions via both the emails, chat box, or even you come to my office in the face. So if you like. So that's all for today. Thank you.